Assalamualaikum warahmatullahi wabarakatuh. My name is Afnan Nafisa binti Muhammad. My metric number 200355.
My name is Aida Zafirah binti Cik Zakaria. My matrix number is 200385.
My name is Muhammad Amir Azamuddin bin Abdul Ghaffar. My metric number is 200238.
And my name is Azra Afrina binti Muhammad Zulkifli with metric number is 198283.
So today we are going to present about X-ray diffraction. In this presentation, we're going to talk about what is X-ray diffraction, Bragg's law, how to get data, method, and the application of X-ray diffraction.
Okay, firstly we look at the history of the X-ray. Of radiation similar to light rays, except that they are more energetic than light rays and are invisible to the human eye. So the German physicist, which is Wilhelm, were accidentally discovered the X-rays in 1845 until 1923. So what is diffraction? Diffraction is the interference between waves that occur as a result of an object in their path. A diffracted beam may be defined as a beam composed of a large number of scattered rays mutually reinforcing each other. So diffraction is a common technique that determines a sample's composition or crystalline structure and a high energy light with a repeating period called the wavelength. Special interference effect called diffraction can be used to measure the distance between the atom, and the interference occur when X-rays interact with each other. So the constructive interference occur when waves are in alignment, the signal is amplified. So the destructive interference occur when waves are out of alignment, the signal is destroyed. And then X-rays are scattered by the regular space atoms. Strong amplification of the emitted signal occur at very specific angle where the scattered wave constructively interfere. This effect is called a diffraction.
Okay, I think you guys were familiar with the Bragg's law equation, which we have learned before in lecture 1, arrangement of atom in crystal. So diffraction of X-ray was discovered by William Henry Bragg and Lawrence Bragg in 1912. Okay, so Bragg equation is derived by treating layers of atom as reflecting the planes. Okay, when we look at the picture, if we think of scattering equivalent to electron from two adjacent parallel planes of atom separated by distance, the angle of constructive interference, which is to produce a diffraction intensity maximum occur between wavelength, is given by the Bragg equation. Next page, please. Okay, so the Bragg equation is 2d sine theta equal to n lambda. The d is refer to the distance separated by the parallel planes. Sine theta is referred to an angle corresponding to a different separation planes of atom in crystal. N is the integer and lambda is the wavelength.
Okay, next I will proceed the technique of the SRD. The first thing first is we have to know the essential part of the diffractometer. The first diagram is the machine that we use in our lab, and the second is the schematic diagram of an X-ray diffractometer. Okay, in the machine that we use is X-ray tube, which is the source of X-ray. Incident beam of optic condition the X-ray beam before its hit of the sample, and then the genometer, the platform that hold and move the sample, and also detector. Net is the sample and sample holder, and then receiving offside optic, which is condition of X-ray beam after it has been uncounted the sample. And then lastly is detector, which is count the number of X-rays scattered by example. The next is first thing first, we have to know the sample preparation for SRD. Firstly is an ideal powder sample should have many crystallite in the random orientation. Secondly, if the crystallite is a sample very large, there will not be a smooth distribution of crystal orientation. you will not get a powder average diffraction pattern. And thirdly is crystalline should be less than 10 millimeter in size to get good powder statistic. And lastly is large crystallite size and non-random crystallite rotation both lead to peak intensity variation. Okay, next is the how it's working, which is the technique is single crystal X-ray. Crystallography has three basic techniques. The first and the often most difficult is the step is obtain an adequate crystal of the material under study. The crystal should be sufficient large, pure in composition and irregular in structure with no significant internal infection such as crack or twining. In second step is crystal is placed in the intense of beam X-ray, usually of the single wavelength, which is monochromatic X-ray, producing the regular pattern of the reflection. As the crystal is gradually rotated, previous reflection disappear from the news one appear, the intensity of every spot is recorded at every rotation of the crystal. Multiple data set have many to be collected, which each of the covering slightly more than half of full rotation of the crystal. And then they typically containing 10,000 of reflection. And the third step is these data are combined computationally with the complementary chemical information to produce a refined model of the arrangement of atom within the crystal. And the final is refined model of the atomic arrangement, now we call as a crystal structure, usually stored in a public database. Next. This is the SRD pattern nanoparticle, which is SRD produce of constructive interference of monochromatic beam of X-ray scattered at a specific angle from each of the lattice plane in a sample. The peak intensity are determined by the atomic position within the lattice plane.
Okay, thank you, Azra. I will continue the presentation on how to get data from experiment. So, as the sample and detector are rotated, the intensity of the reflected X-rays is recorded. The detector records the number of X-rays observed at each angle 2 theta. Then, constructive interference and peak in intensity occurs. A detector records and converts the signal to a count rate. So, this is the example of X-ray diffraction graph. The intensity of the peaks is related to the amount of molecules in that phase or with that spacing. The greater the intensity of the peak, the greater the amount of crystals of molecules or molecules with that distinct spacing. The width of the peaks is inversely proportional to the crystal size. A thinner peak corresponds to a bigger crystal. A broader peak means that there may be a smaller crystal defect in the crystalline structure or that the sample might be amorphous in nature. From the X-ray diffraction pattern, we can determine the defects, crystal structure, crystalline size and microstrain, texture orientation, residual strain, quantitative analysis of phase composition, unit cell parameters and Bravais lattice symmetry, and the last one is identify amorphous material. So there is three significant of peak shape in X-ray diffraction. The first one is peak position, determined by the size and shape of unit cell, which is this spacing and systematic absence. Second, peak intensity, determined by the atomic number and position of the various atoms within the unit cell. And the last one is peak width, determined by instrument parameters, temperature, crystal size, and strain. So why some peaks in X-ray diffraction pattern have high intensity than others? First, some peaks have high intensity because there is more periodicity than other directions. The peak will be high if there is preferred crystal orientation. Peak will be low if crystals are arranged in random order. Second, the higher the electron density variation, the higher the intensity of the plane reflected in X-ray diffraction pattern. Peak intensity represents the atomic position in the crystal structure. For example, if an atom in phase centicubic crystal structure moves to body centicubic crystal structure, then the intensity will disappear.
Alright, next we go to the X-ray diffraction method, which is we have three methods. The first one is a powder X-ray diffraction. The second one is a single crystal X-ray diffraction, and the third one is X-ray diffraction at the synchrotron sources. Okay, the powder X-ray diffraction is used mainly for phase identification and the determination of lattice parameters and lattice type. The single crystal X-ray diffraction is allow the structure of molecules and extended lattice to be determined. And the X-ray diffraction at the synchrotron sources have a high intensity X-ray beams generated by synchrotron sources allow the structure of very complex molecules to be determined. And then the principle of the X-ray diffraction, an X-ray beam striking a polycrystalline sample is scattered in all directions. Each set of planes of atom with lattice spacing d give rise to a cone of diffraction intensity with a very large number of crystalline these rays merge together to form the diffraction cone. A powder diffractometer uses an electronic detector to measure the angles of the diffracted beams. The scanning the detector around the sample along the circumference of a circle cuts through the diffraction cones at the various diffraction maxima, and the intensity of the X-rays is recorded as function of the detected angle. This is the example of a powder diffraction pattern collected on an energy dispersion detector. Okay, they have a strength and limitation of X-ray powder diffraction, which is the strength is powerful and rapid, which is less than 20-minute technique for identification of an unknown mineral. The minimal sample preparation is required and data interpretation is relatively straightforward. The limitation require tens of a gram of material which must be ground into a powder. And then the peak overlay may occur and for high angle reflections. This is the video on how the powder diffraction works. Okay, next is the single crystal X-ray diffraction. The principle of the single X-ray diffraction is the collection of diffraction data from a single crystal can be carried out by using a diffractometer. The crystal is rotated around 3 orthogonal directions, and the force diffractometer use a scintillation detector to measure the diffracted X-ray beam intensity. The analysis of the diffraction data from single crystal is formally a complex process. Okay, they have a strength and also a limitation for single crystal X-ray diffraction. The strength is there are no separate standard required, non-destructive, detailed crystal structure including unit cell dimensions, bond length, bond angles, and site ordering information. Determination of crystal chemical controls on mineral chemistry, and with a specialized chamber structure of high pressure and temperature phases can be determined. And the limitation is must have a single stable sample, generally between 50 until 250 microns in size, optically clear sample. Twin sample can be handled with difficulty, and the data collection generally require between 24 and 72 hours. Okay, this is the X-ray diffraction at synchrotron sources. The synchrotron radiation is produced by electrons circulating close to the speed of light in a storage ring. Because of their size, synchrotron X-ray sources are normally national or international facilities. The diffraction equipment located at such an X-ray source permits the study of much smaller samples and crystals as small as a 10 times 10 times 10 micrometer. The data collection can be undertaken much more rapidly and more complex structures such as those of enzymes and can be determined more easily.
All right, for the neutron diffraction. Okay, basically, neutron and electron traveling at suitable velocity and thus undergo diffraction by crystalline inorganic compound. Neutron beams generated by moderating neutron generated in nuclear reactor through spallation process. Moderating means it's slowing down the process. Okay, next. All right. The advantages of using neutron diffraction. First is neutrons are scattered by nuclei rather than by the surrounding electron. As you know, neutrons are sensitive to the structural parameter that often complement those for X-ray. Scattering is not dominated by heavy element, which can be a problem with X-ray diffraction for most inorganic compound. It will be a problem for the X-ray diffraction to detect light electron if the element contain electron-rich rich atom of metal, or we known as heavy element. So, for example, if we want to locate the position of light elements such as hydrogen, lithium in the metal that also contain plumbum. Next slide. Okay, as we know, the plumbum is an electron-rich metal atom, so it can be impossible with the X-ray diffraction, as almost all electron density will associate with the plumbum atom. So with neutrons diffraction, in contrast, the scattering of light atom is often similar. So the light atoms contribute significantly to the intensities in the diffraction in the diffraction pattern. So it will be easier to detect the light electron in the cases. Okay, next please. Okay, next, the advantages is to distinguish nearly isoelectronic species. Okay, in the periodic table, there are pairs of neighboring elements. In the periodic tables like oxygen and nitrogen, chlorine and sulfur. These neighboring elements are nearly isoelectronic. So it scatters X-ray about to the same extent. So they are hard to tell apart in structure that contain them both. So it's hard to identify the atom if we don't using the neutron diffraction. However, the atoms of this pair can be scattered neutron to very different extent. Nitrogen is 50% more strongly than oxygen, and chlorine is 4 times better than sulfur. So the identification of the atoms is much easier by X-ray diffraction.
Okay, next I will explain about the uses and application of X-ray diffraction. Okay, next. Okay, first thing first is uses of X-ray diffraction. X-ray diffraction is a powerful non-destructive technique for characterizing crystalline, and then it's provide information of structure, phases, and prefer crystal orientation, also other structural parameters. And lastly is determination of system isomerism. Next. This is some as application of X-ray diffraction in our industry, which is the firstly is petroleum industry, and then the polymer crystallization, ceramic and glass manufacturing, and also metallurgy. Okay. That's all from us. Thank you.
we use X-ray diffraction to do this. XRD can identify thin film materials, analyze crystal structures, detect defects, and more. In other words, it gives us material characterization. This is an image of the XRD system we have access to. The X-ray tube, also known as the source, is what produces the X-rays. This works by having tungsten filament emit electrons. The electrons receive an applied voltage, which makes an electric field and accelerates the electrons, as well as directs them towards the X-ray target material. Electrons bombard the target atomic structure, causing secondary electrons to be kicked out of the electron shells. Holes in the electron shell caused by secondary electrons being expelled leave it in an unstable state. Electrons from higher energies will drop down to fill the space, releasing energy in the form of X-rays. The primary optics contain solar slits and divergent slits. These allow for better resolution of angles, so we can see the film more precisely. This allows us to see narrower peaks if they exist in the film, but do not cause narrow peaks. We want narrow peaks because that means there is a high concentration of atoms with the same spacing. This image is of some data with 2 peaks. These are the peaks that we were talking about. Secondary optics receive deflected rays. Monochromators filter out unwanted X-rays. The detector converts X-rays to visible light, which is called scintillation. X-rays contact a compound that absorbs X-rays and emits visible light, then produces proportional electrical voltage. The equation helps us calculate the distance between layers of atoms, or the scattering angle of X-rays hitting a crystal lattice and deflecting off. The equation is 2d sine theta equals n lambda. In practice, n is almost always 1, so we can drop that out of the equation. This works by having an X-ray contact an atom and deflect off. We can make angles out of this. Let's call this angle theta. For the X-ray that contacts the lower atom, it travels an extra distance. I'll add perpendicular lines from the beginning of the extra wave. We will call the lower points x, y, z. So for example, this bottom left angle or incident angle is say 30 degrees. If we know our extra wavelength, we can calculate distance now. We know the 30-degree angle plus the other angle must be 90 degrees, so the other angle must be 60 degrees. So we can now determine that the final angle is 30 degrees, the same as the incident angle. So these two angles are always congruent. We can now use the law of sine and calculate the hypotenuse, which is the distance between atoms.